Hey guys, welcome back. Quiz 2 hopefully went well. It's okay if it didn't. First two quizzes of the quarter, just trying to get, the hang of it, trying to get used to it. We have many other opportunities to show in this quarter that we can, we know the material we do well. So don't worry too much about these first two, but let's lock and load for these next couple ones. Just to get this out of the way, I imagine this video is going to be long. I'm already anticipating more than 2 hours. Just because, this is how the quarter is. It ramps up the amount of material you need to know. You can start to feel like you need to know a lot between quizzes, which is that's just how it is. So one thing is I'll start to focus more on the most important parts. I won't go through everything. Not that I won't touch everything it's more of like I won't spend as much, in-depth time on things. A lot more important to get through the most of the material and just the core concepts. But I'll do my best to make sure not to spend any extra time on anything. I already know the first part. There's gonna be one section, doesn't take a lot of time, so I'll try to get to that section as fast as possible so that we can get through that. But yeah, I'll probably call a break halfway through this, and that's a good point for you guys too to take a break, because again, above all else, your health is what matters. If you're not healthy, then you're not going to be learning very well. So we'll probably have to do that. But today we're going to talk about benzene and its reaction. So we just spent a whole 2 hours last time and last week kind of learning about what is this weird, strange being inside of benzene, right, that makes it so stable, and that's aromaticity. And so because it's aromatic, it's stable, it doesn't really want to do things. For the most part, it's not really going to do a lot of the traditional reactions that we've done before. So back in 8A, you guys learned reactions like HBr, right? You do this, room temp, maybe like a couple hours, nothing's going to happen, right? Because, for it to become this compound here, let's say we add H and Br across one of the pi bonds, you've effectively destroyed the aromaticity that you've made, which is not a good thing, right? So we want to retain the aromaticity of the system. With that being said, though, then, right, there's got to be a way to trick benzene, right? Benzene isn't the smartest thing in the world. It doesn't have a brain. It just has electrons, and electrons are going to move when you really, really motivate them to move. So the general trend, or the general mechanism that we're going to see with a lot of these benzene reactions, all of them really, is we're going to form some kind of super electrophile. Okay. Again, benzene, it is stable, right? It doesn't really want to play with a lot of the electrophiles you would normally have available to you. But you give it something super electrophilic, something so starved of electrons that it just makes sense to give it electrons. You feel bad for it. And you can even trick benzene into taking an electrophile. Okay. And so we'll get to this intermediate here, where we have added the super electrophile and formed this cation species. Now, again, this cation species is particularly stable, right? Because we have 3 resonance forms that stabilize it. I know a couple of you guys are having issue with, resonance and how to visualize it and stuff. The nice thing about 8B is that you don't really need to know everything. You don't need to really remember everything. You just have to remember the things that I've shown you or that you've seen in lecture. So something like this, if you're having a hard time seeing how this resonates, right? I could draw in the arrows too. So I'll go ahead and do that. Right, like this would push here, right? This would push here, or, oh, sorry, actually I did it one at a time. So that would push first, and then this would push, right? That's kind of the arrows going on there. But again, if that's troubling for you, that's okay. You just have to kind of remember what we've done, what's being done in front of you. You don't have to go out of your way to remember all that stuff. But yeah, this cation is particularly stable, but again, it's not as stable as being benzene. So in order to become benzene again, this hydrogen that the electrophile carbon has, right, that hydrogen's just taken. And what we return back to is the benzene, but now with this new electrophile added on. So we have a name for this. We call this electrophilic aromatic substitution, because we're substituting the hydrogen with the electrophilic group. And this is an aromatic ring. So really, this is, you can take this application or this reaction applied onto many of the different aromatics. Hopefully now the title of the video now makes sense, right? Because we just by shorthand call this EAS. but yeah, this is going to be the general pattern. So I'm not going to go out of my way to draw the mechanism every single time. But the one thing we will always draw is how do we make the super electrophile, because that's really the bulk of the mechanism. This is always the same across every single mechanism. It's always attack the electrophile and then eliminate out a hydrogen, right? Go back to aromaticity, restore the aromaticity. So all the mechanisms that we're going to talk about today, the important part that you guys should go out of your way to remember is this part here, is making the super electrophile, right? Making that toy that your shibazine really, really, really wants to play with, because it's like, oh, whoa, that's that's an interesting thing there, right? Yeah, cool. All right. So what are our different class of reactions that we can do? So normally I don't do this, but I think it's actually useful to actually break down the reactions beforehand so that you guys can see what the different reactions are and how I break them up, and maybe help you guys, start to break these up too. Really, when it comes to having a lot of reactions between quizzes, the most important thing to remember, or the most important thing to apply, is, patterns. Figuring out the pattern so that you don't have to memorize 10 different things. Maybe it's more so that you memorize 3 things, that those 10 different things, follow the pattern that they follow. Okay. Now there's technically 5 reactions you need to know in a benzene. But if you really think about it, there's 2 types of mechanisms that involve two different sort of catalysts, or 2 different reagents. And as long as you understand the generic pattern for both of them, you'll know how to do all 5 of these reactions all the time. Okay. So one side I call the dehydrations, which involve H2SO4. So this is HNO3, H2SO4, and then SO3, H2SO4, which respectively on any carbon of these, this is actually one thing I get asked all the time. Doesn't matter which carbon something goes on. When it's a naked benzene, or a benzene with nothing on it, right? It doesn't matter. Just put it on any carbon. So I'll just put it there just for the sake of it. And this one I'll just put here, again, just for the sake of it. It can go on any of the carbons. But this is what both these reactions do, is they install either an SO3 group or they install an an NO2 group. Okay. And I call these the dehydrations because, as we'll see in this reaction, both of these are going to lose water. In their mechanisms, both of these lose water. Okay. And so the name of the game is, how do I make water with these reagents, right? Whether with the H2SO4 or with the HNO3, how do I make water with them? Okay. So maybe you can start thinking about how you can make water from them. And maybe down here, what I'll do is I'll just put the structure of these reagents. So for anyone who wants to go ahead and start thinking about that, you can totally do that. So you can start thinking about how can you possibly make water from one of these, from both of these, sorry. On the other hand, here what we have are the Lewis acid catalyst reactions. And so these will always have some kind of metal halide. Usually you'll see AlCl3 or like FeCl3. Doesn't really matter. I'll use both, but keep in mind that, again, it does not really matter which one you see. But there are 3 types of these reactions. There is the X2, there is the haloalkane, and then there is the acyl halide. Okay, so one thing you'll notice here is that halogens essentially always show up in these. We either have a halogen in the reactant, right? So in the Cl2 or in this ethyl chloride, or we have it in the metal, right? In this case, we have it in the AlCl3 or the FeCl3. Okay, again, these guys will return, in this case, a chloride on any carbon. This one is a really easy one. If you want to learn a trick right now and never have to worry about acylations ever again, actually, there's 2 steps here. So I'll put that there's 2 steps actually, right? All you got to do is take whatever's on the acyl group. So let me show you this little trick. You take whatever's on the acyl group. So all of that, get rid of the chloride. So I erase the chloride and then just put the benzene ring in its place. And that's how you do an acylation in 2 seconds. So if you almost wanted to, you don't even have to really watch the rest of the acylation part, right? That's literally how you do acylations. It'll always work like that. You just replace chlorine with the benzene. Okay. Alkylations are kind of the same, but there is a couple things about this that makes it a little bit, bad. So we'll talk. This is what I was talking about when I said earlier that there's going to be a part that takes a long time. This is the reaction that takes the longest. Okay, so I imagine majority of the first hour will be all on that. Okay, hopefully we can contain it in the first hour. If we can, we'll be right on track actually, because the second part of this video is not too bad. Cool. So again, 5 different reactions. So it feels like you need to know 5 different things, but really you just need to know 2 types of things. You need to know how to do a dehydration, and you need to know how to use the Lewis acid catalyst. Okay. So let's go ahead and let's see how this works. Okay, we'll start with the dehydrations first. So like I mentioned, dehydration, right? H2SO4. We're just going to pull water out of it. So let's say that we're doing the reaction of HNO3 and H2SO4, right? Again, benzene needs a super electrophile. It doesn't just react with anything. So in neither of these cases is the benzene going to, in either of these acids, neither of these acids are going to react with the benzene, right? But when these guys are mixed together, they can make a super electrophile that might entice the benzene. So if I go out and draw this HNO3 here, I'll go ahead and draw an H2SO4. Okay. Like I mentioned before, right? From one of these reagents, we want to make water. Now, both of these are acids. So you might be thinking, well, I mean, aren't they acids? So they just protonate something. Should they, protonate something that's not an acid? Remember that acid-base chemistry is very, very general. It's very, very relative. So although these two are known to be strong acids, right? One acid is going to be stronger than the other, right? That's just always the case. One is always better than the other. And so that thing will be the acid, and the other thing, relatively speaking, is more of a base. So knowing which one of these two is going to be the acid really helps out, right? Which one's the stronger one? In that case, it's going to be this guy here, okay? So the acid of this reaction is H2SO4, which means that this guy has got to be our base, right? I know it looks like an acid. I know it tastes like an acid. I know it smells like an acid. But hey, in the context of the reaction, right, the fact that it is generally a weaker acid, it makes it a stronger base. And so this is what's going to take a proton from this guy over here, okay? So again, how can we make water? Where can we make water, right? Which oxygen are we going to use? 3 of them, right? Which are we going to use? The easiest one to work with is this guy here, right? That guy's already an OH. So by all means, just go ahead and pull that guy's proton right off, right? Again, this is acid base, so we can use double-headed arrows if we want. We don't have to. I'm just going ahead and do that because I imagine you'll see that in class too. Okay, but what we get is this. And then, just like with alcohol chemistry and ether chemistry, anytime you make that water molecule, what's going to happen? That water is going to fall off. I mentioned this. Remember I said, we're going to ask this question a million times this winter. When I make water, what happens? When you make water, water falls off, okay? Now here's the cool thing. The way that we can help this water fall off and completely make the electrophile is actually this O- comes in and donates electrons too. So this O- helps to push out that water, okay? And what we get out of this is the NO2 electrophile. Now this guy, super juiced, super juiced. Or actually lack thereof. It's not juiced at all. If anything, it's thirsty. This thing is super thirsty. You have a nitrogen, cationic nitrogen in a pi bond with 2 oxygens. You can imagine that this is basically 2 O-. This nitrogen is super electrophilic. It needs electrons quick. It needs electrons fast. Okay. So this here is our super electrophile. So if we wanted to, we can almost even erase this and say that really what this is NO2 plus. And this is what benzene is going to attack. Oops, sorry, not E, NO2. This is what benzene is going to attack in order to make the nitrobenzene. Now, I guess we could draw it out so you guys can see the full arrow push, right? But this is how it would look in case you need to see it. Okay. But again, this cation here, it's stabilized. I'm not going to draw the resonance forms because we already did. It's always the same. The point is that at some point in time, right, that HSO4 minus that we made earlier, right, will just pull off this proton, right, and we'll restore the aromaticity. Okay. There you have it. We have a nitrobenzene. Okay. So we can nitrate our benzenes. All we have to do is make the NO2 electrophile, super juiced. Super wants juice. It's very thirsty. Okay. Again, that idea that, hey, we can have 2 acids, but one of them is just going to act as a base, right? As long as we can pull off that water, everything will work out. Okay, cool. So that's the NO2 reaction. Again, any of these carbons could have participated. I just chose the rightmost one or top right, just because that was just my choice. You could have also drawn it here. Again, as long as it's a naked benzene, choose wherever you want. It's not going to matter where things go. But if we were to nitrate, let's say this thing here, let's say we were to do the nitration reaction here. This is going to matter where we draw it specifically. Okay, I'll give you a little, sneak peek. It's actually going to go here if we do it again. Okay, but just something to keep in mind. Okay, cool. So that's nitration. Again, make that water, pull it off. If I then move on to sulfonation, right, then this reaction shouldn't be too bad. It should make sense how we make the electrophile here, as long as I give you guys the two components, right? We have 2 sulfuric acids, right? And we have to make water. So what are we going to do? If you want, you can pause and try it on your own. Hopefully it's not too hard to see. We're just going to do the same thing we did last time. If we just pretend this guy is like the NO2 or the NO3, right? This guy is just going to pull off that proton. Sorry, not the oxygen. It's going to pull off that proton. And then this oxygen is going to help assist in kicking that water off. And what we get out is the SO3 electrophile. Okay, the SO3H electrophile, I should say. Okay, so look at that. All we do is pull off water, right? As long as you remember it's a dehydration, you pull off water, you can make the electrophile in 2 seconds. That's not too bad, right? Now, one little cheeky thing is that technically you already do have SO3. So, in a sense, what you could have done also is just protonated from here. I'll just tell you guys this. Some professors don't like it when people do that because they want you to show how to make the electrophile. That's kind of the point of the unit. So I can't guarantee that if you did this on an exam for a mechanism question, if you guys even get those anymore, that you'll get the full points. But it is, cheeky way of doing it. Technically, you do already have the SO3, right? But it should be SO3H plus, right? That's what the active electrophile is. So again, I can go ahead and replace this here, make that attack. One cool thing actually is that the SO bond, we draw as a double bond, but in reality, it's actually really an it's an S plus O minus single bond. This is such a polarized bond that really sulfur is a cation. So if you imagine 3 of these on a sulfur, really this is S3 plus and then O minus, O minus, O minus, which, I mean, if you wanted to think of the, an electrophile, imagine a 3 plus electrophile. That's insanely electrophilic. Okay, so if you want a cool little fact to impress your friends, text your mom, let her know that sulfur is a super electrophile because the SO double bond is actually an SO single bond where S is plus and O is minus. Okay, cool. So definitely super electrophile. We are convinced it's a super electrophile. Okay. Once again, actually just to kind of do things a little differently, we'll put it over here, whatever. Right? We'll do that. Let me draw it out actually. Okay. And then once again, there are resonance forms. I'm not going to draw them because I've already drawn them once. I even recommend that you guys only really draw them once on your note card. Don't draw all of them every single time. It's a waste of time. But now we have the SO3H molecule. Okay, so this is how we sulfonate. Now, sulfonation is a little interesting. It's a little different from the rest of the reactions. You might have noticed that back here, I gave reversible arrows here, but I kind of said this was irreversible. So to some extent, this reaction always goes to the NO2, and then we always add on the NO2 and we call it a day. Well, what's really cool about sulfonation is actually it functions on an equilibrium. Actually, every reaction does. It's just that this equilibrium is very, very, measurable, very, very advantageous. We can use it to, use it to our advantage. So what can we do here? Well, if I put in a lot of SO3 into this H2SO4, I will get my sulfonation. But if I put a lot of water in my H2SO4, so I use a dilute acid, turns out that we can actually reverse back to the hydrogen. So this is actually a very, very useful synthetic reaction at the higher level because sulfur always likes to add in a particular way towards other groups. And so we can use it as what we call a blocking group or a protecting group. Something we can do is pretty cool. Again, not something that we need to know at the 8 level, but we should know that this functions on an equilibrium. So you could be given a series of reactions, right? So as we'll learn, you can do 2 reactions on a benzene step by step. Maybe the first one's SO3, the second one's like Br2 or something, right? And then that last step can just be an H2O, H2SO4, right? And that will indicate to us, oh, we're getting rid of the sulfur group, which would be kind of weird to do, considering we added it first in the first place. But it is something to know. This is a reversible reaction, and one that is taken advantage of. So there is synthetic utility here. Cool. So those are our two dehydration reactions. Again, whole point there is that we can add our electrophiles because we pull off that water, make that super electrophile, and benzene just has to attack it, right? It's forced to do it. Now, keep in mind that it's really important that these are the conditions we have, right, for this reaction here. If I were to try to do this reaction and let's say just HNO3 or just SO3, this is not going to work, right? We need the H2SO4. That's a requirement. That's kind of why I named these after the, that acid catalyst that you need. This reaction won't work without them. Okay. So make sure that, you have both of these on your arrow, right? If you want to do this type of reaction. Okay, cool. All right. That was pretty quick, actually. Those two, I mean, those aren't very bad. It's not really much to understand there, right? You just dehydrate them and you add the electrophile. So let's get on to the metals, the Lewis metals or the Lewis acids, right? And let's see what's going on there, right? How do these guys work? Okay. So the first reaction we'll start with is the halogenation. That one's pretty straightforward. So again, if I just have Br2, you guys don't really learn this reaction, I don't think, but Br2, you add it to a pi bond, it just adds two Brs, right? So if you try to do this reaction with just Br2, maybe in CH2, Cl2 or something, nothing's going to happen, right? You're not going to get any kind of reaction there. But if we add in a Lewis acid like AlBr3, so we're just matching the halide to the Lewis acid here, something interesting will happen. Okay, so again, just like before, right? In the sense that we had an acid and a base, we also have the same thing here. We do have an acid and a base here. Now y'all might be wondering, oh, dude, are you just like imagining hydrogens or something, or like what's going on? It may not be super obvious, right? But this is an acid base on the Lewis level. Okay, so back here, what we did was acid base on the Bronsted-Lowry level, which is, the acid base that concerns proton transfer. This is the most recognizable, most iconic Bronsted-Lowry type of acid base type of reaction, right? The Bronsted-Lowry. But really, the most rudimentary, the most bottom level foundational form of the acid base is the Lewis acid base equation, right? And so how does this work? Well, Lewis acid base chemistry simply just dictates that if you have something with electrons and something that wants electrons, so that doesn't have electrons, right? So I don't want to use A and B here. Let's use, or if I use, let's use it this way, right? If I have something with electrons like a base, right, and I have something that needs electrons like an acid, right, the base can donate those electrons to the acid. That is the Lewis acid base sort of definition. Okay, so an electron donator gives electrons to an electron acceptor. Okay. So if I look at the two things I have on the screen, I have a Br2 and I have an AlBl3, right? Between these two, I mean, I've kind of drawn it in just to kind of key it in, but the Br2 has these electrons that can function as a base, right? Maybe not a traditional base like OH minus, but definitely on the Lewis level in terms of being an electron donator. And if I look at AlBl3, I have a metal, right? Now, this metal has 3 electronegative things on it. You can imagine that there is a dipole going from the metal to the electronegative thing, right? That metal is looking to really accept some electrons, especially with those 3 things, those 3 electronegative things on it, right? So it's like a delta positive 3, right? So this is a very good acid or a Lewis acid. Okay? So we're doing acid-base chemistry here just on the Lewis level, where the bromide or the Br2 is going to attack the aluminum. So what we get out is this here. Now this is where people get a little confused, so it's okay. Just kind of remember this, or work on understanding the charges. Doesn't matter. I would just say write this down. But whenever you do this attack here, the aluminum, because it gained electrons, becomes minus. Bromide donated, it lost an electron, and becomes positive. Okay. So we make this adduct here. Now you can imagine, right, that this bromide is very electrophilic, right? So a very common thing to think here is, oh, that's the bromide that we attack. But remember, in organic chemistry, nothing is static, right? Formal charges are just formal. They're just telling you where electrons, in terms of counting where they are, right? But what we want to know is, how does this positive influence the system? Well, because this bromide is so positive, right, and it wants electrons very, very badly, you can imagine it starts to pull on its bonds like crazy, right? It starts to take electrons in like very, very quickly, very, very strongly. So this bromide down here on the left actually becomes very, very, very electrophilic because it's being, forced to give up its electrons to the bromide, right? This bromide has a headache, right? It's stealing pills from this bromide here, right? It's taking that bromide's Excedrin or whatever you have to use for migraine control, right? So in fact, actually, despite the fact that there's a positive here, right, the bromide that we actually attack is the one right here. Again, all because of the dipole that results from that bromide being positive. Okay, so I want to redraw this here. Minus positive, right? Super electrophile is actually going to be the bromide. That bond breaks. And again, what we get out, oops, put the bromide here this time, this species here. Okay. Again, this will resonate, but I'm not going to draw that out. This one bromide that was on the Lewis acid, so AlBO4 minus does leave off of this. That one bromide that we added on, go ahead, take that hydrogen, and what we get out is the halobenzene, or the bromobenzene in this case. Okay, cool. So this is the general pattern for the Lewis acid mechanisms, right? Generally speaking, I'll have some kind of species with a halide on it, where the halide attacks the metal, right? That in turn makes the halide positive, but it doesn't make the halide an electrophile. So the bromine that's the bromine that's positive is not the electrophile. It's always the group attached to the bromine that becomes electrophilic because of that induced dipole. Bromine, right, doesn't want to be too positive. It wants electrons more than anything. So that induced dipole is what makes the group on the bromide a lot more electrophilic. In this case, the X is just another bromide, right? So in this case, it's just bromide that's doing this. So that's why we get the bromide there. But as we'll see, I mean, if we go back here, we can see that that group can change, right? It can be a chlorine. It can be an alkyl group. It can also be an acyl group. So hopefully now you can see why these guys are adding on to the benzene. It's because we're that activation from the Lewis acid. Okay. Again, you can also use other halides, right? Like it's not, there's no rule saying it has to be bromine. I could have also used Cl2, FeCl3, or AlCl3, doesn't matter. I'm just using Fe now because I haven't used it yet. But this would just add chlorine right to one of those carbons. Again, going through that same activated chlorinium, or chlorinium? Chloronium. I don't know what you would call that. Okay, exact same idea. So again, activating this chlorine because this chlorine is positive. Okay, cool. So those first three reactions are usually, very, very simple to understand, right? Again, it's just understanding what the mechanism is doing and what you're effectively adding to the benzene ring every single time, right? Either you're adding, NO2, you're adding SO3H, which actually, let me draw this out so you guys can see that. Sometimes professors will draw it out, so it's a little hard to tell what it is, right? You can add a bromide, a halide, right? Usually, usual suspects is chlorine and bromine. Fluorine and iodide are kind of the weird, the odd ones out, right? We don't normally see reactions with those guys, but those are our usual suspects. Okay. So then let's take this metal idea, right? This idea that we can add halogens via Cl2 and this metal, and let's change the halogen out for an alkyl chain. So let's say that I wanted to add in CH3Cl, right? The concept is there, isn't it? We have a halide that can function as a Lewis base, right? Attacks the metal. And then again, the halide, despite being positive, that's not the actual species that the benzene wants. What it wants is the species that activated via induction, right? This chlorine here, right, pulling on that bond with carbon is going to make that carbon a lot more electrophilic, and that's what benzene's going to want. And that's exactly what we see. Okay. So we can also make alkyl reagents. These alkyl electrophiles are pretty good, right? Because benzene goes ahead and attacks it. And what we see is the addition of a CH3, which again resonates that cation, but who cares? We've already seen it once, so we've seen them all. So what we get out is this here. Okay. This is known as a Friedel-Crafts alkylation. Okay, Friedel-Crafts alkylation. That's a term you guys are going to get very, very used to seeing. Okay. Again, the thing that takes this will be the chlorine. Okay, from that species, from the FeCl4 that we generated in this step. Okay. So look at that. We can do an SN2 type of attack on this substrate, right? And the reaction works pretty well. I mean, if we take this over to the ethyl version, so let's say that I take this over to this, because we're like, okay, methyl works and it's SN2 on the methyl. Let's check with the ethyl chloride, right? If I turn this into this, how well does this work? And then this also works pretty well, right? This also is an SN2 attack. I'm just going to draw the result here, right? The result is just that I add this ethyl piece to the benzene ring. Okay. So this reaction, it seems like the best reaction ever, right? Looks like we can literally just alkylate on the benzene, and nothing should really go wrong here. So what happens then if I take this same reagent, but I use a propyl chloride? Let's use the Al this time, because I don't want you guys to get, into the thought process of only Fe. What happens here? Well, you can imagine that we will get this adduct here, and then supposedly benzene should just attack at this position, right? So supposedly, what should result is this propyl piece here, right? And so this should be our major product. I think that makes sense, right, when you first think of it. But if you were to actually do this reaction, this is not the product you see. Sorry, this is not the product you see. In fact, the product that we see, so actually let's keep this up, right? This is not what we see. You might see a little bit of that, but the major product of this reaction is actually this. It's isopropyl benzene. Okay, that's weird. Because if I look here, I see propyl, right? I see, we call this N-propyl when it is the straight chain, not an isopropyl. So what in the world is going on? Why is it that we're activating that secondary position instead? Well, it turns out that when you do Friedel-Crafts, this reaction actually is not very SN2 like we would want it to be. So I know back in 8A, we kind of learned systems that always did SN2 or always did SN1 or E2 and E1. Turns out in real life, everything is a mix of everything, right? Every reaction is competing. Every mechanism type is competing, right? It's all about understanding which conditions might favor one reaction over the other. And so it turns out that instead of benzene going ahead and attacking here, there's actually an internal attack that happens first. And that internal attack is from this hydrogen on the secondary carbon, right? When this hydrogen internally rearranges or attacks here, right, displaces out the chloride, what we get is this secondary cation here. Now, whoa, that's kind of crazy, because if this is a cation, this means that we're following SN1 mechanics. So why is it that earlier we didn't see any sort of SN1 mechanics whatsoever? Well, if I look at the CH3Cl, right, and let's say that, I put in MX3 and I try to imagine what the cation would be. That there is a methyl cation. And methyl cations are one of the most unattainable, cations in the world. It is the most unstable cation, right? One of the most craziest things that you could draw on your piece of paper and expect to get points for, right? So the reason why we got that sort of SN2 vibe with this reaction is because, hey, SN2 is the only thing that could happen. In terms of competition between SN2 and SN1, SN1 was completely off the table. You can't even make the intermediate for SN1. So how could you even tell that this was an SN1 type reaction if you couldn't even make the intermediate? This reaction was forced to go through SN2. Okay, so methyl chloride, again, didn't do an SN1 because, hey, if I tried to do this, trying to make a cation here, it wouldn't make sense. But I could do an SN2. That does make sense. Methyls are the best for SN2. Okay. And the same thing for this guy here, right? If I try to do that same sort of shift and say, okay, well, I could, I could maybe do a shift. Well, hey, guess what? That shift just makes a primary cation. And if I just lost the chlorine, let's say that I just lost the chlorine, just like I thought about last time. If I just lose the chlorine, I also just make a primary cation. So the methyl and ethyl chloride variants of this reaction had to be SN2 because the SN1 versions just were never going to work, right? SN1 is just never going to work because you can't make a primary cation or a methyl cation for that matter. But you turn this into any carbon chain that's longer, right? So anything that's propyl or longer. So 1, 2, 3, anything like that. And now you've suddenly invited the possibility of having a rearrangement, because with this rearrangement, what we get out is a secondary cation, which I know that last quarter we said was not possible, but that's okay. Just rewrite it in your brain, right? It is totally possible to make secondary cations in this class, and we will make them all the time. So really, the Fredo-Crafts alkylation reaction is an SN1 reaction, right? If you give it time to think and you give it time to form a stable intermediate, it will. And that stable intermediate is the cation, right? That's kind of weird to say, right? Cations aren't stable, but relatively speaking, right, it is going to be stable in this case. Okay. So really, if these are SN1 type reactions, we should always be looking out for these type of rearrangements. And so when we do these reactions, I always recommend, again, if you see anything longer than propyl, right, anything longer than propyl, always, always, always consider there's a rearrangement, right? So for example, this reaction here, right, I can see that this is 1, 2, 3, right? I know there's this fourth carbon here, but it's, it's not part of the main chain, so it doesn't matter, right? I mean, and it doesn't matter which one of these you choose, really, right? They're both the same. But 1, 2, 3, I see something that's 3 carbon, carbon chain long. I'm going to think that this is going to rearrange. Okay, so how can I think of this? Well, what might be useful for those of you that have a hard time drawing these kind of things is what you can do is you can draw the chlorine reagent out. You can replace the chlorine with the positive, and then draw out the H that's going to do the rearrangement, right? So that H that's next door, that's going to move, right? In this case, all you have to do to draw the correct reagent that's going to be attacked is you switch the cation and the H. So the H goes here, the cation goes here, and then you can erase the H here. Okay. So if you have a hard time visualizing these rearrangements, that's an easy way to think of it, right? That's just an easy way of doing it. Is you switch the H and you switch the cation, right? Now you have the active ingredient that's going to add to the benzene ring, okay? Because that's what benzene is going to attack. It's going to attack this tertiary cation. It's going to form this here. Okay. Again, let's say that I have like this thing here, right? Actually, no, let's not do this one. That one might be a little hard. But let's say we have this butyl, right? Again, it's longer than propyl, so I know it's going to shift. So what do? I go ahead and I draw this without the chlorine. I put a positive there. I have this hydrogen here, and I know it's going to switch. It's going to look like that. And so this is what the benzene is going to attack. Again, we can get rid of that. Benzene is going to attack this group here, right? Again, if you're more comfortable with it, you can draw these anywhere, right? The first edition can go anywhere. So if you're more comfortable with it, maybe it's easier for you guys to see that it would look like this, right? And you can draw on that bottom carbon. You don't have to necessarily draw it up here and be like, oh, did I draw the right thing? I can't tell, right? That's always a bit of an issue. Sometimes people have a hard time seeing that. Okay. It's another one that can rearrange. That's a good one. Oh, I guess this neopentyl one. This one's a bit tricky. Neopentyl chloride. In this case, right, it's not a hydrogen that shifts over. Right, it's actually one of these methyls. So you can, again, replace this with a cation, and then it's switching with one of these CH3s. We'll switch it with this one. Like that. And so that's this is the active ingredient that we're going to be adding in. So that'll attack there. That's a bit difficult to visualize, maybe? No, I don't think so. Is it? Hopefully you can see that it's just that, essentially. Again, as long as you draw the correct answer. I know this looks like it looks like a bond angle hell, but it's okay. It's the correct answer. Who cares? That should be fine. So again, anytime you have these N systems, right? N alkyl systems of just long linear chains, always look out for that hydride shift. Always look out for that, or even a methyl shift, right? Like you can even argue that if there was like 2 methyls here, it would just do a methyl shift instead, just like we saw down here, right? I'll actually even, just because we mentioned this one, let's just do it, right? This chlorine, replace it with a positive, and then we're going to shift it, right? So we'll say that that methyl there that I drew will shift here, the cation will go there. Okay, so that's what's going to add in. Okay, so hey, there's rearrangements, so that's kind of an annoying thing. But again, fundamentally, this is an SN1 reaction. So that means that if you can form a cation, generally speaking, you can form a very good Friedel-Crafts electrophile. So for example, right? Hey, maybe we want to take advantage of this. Maybe instead I purposely do the terbutyl chloride here, right? Again, this is going to attack the metal, and this is going to fall off immediately because what we get out is that tertiary cation. So this can be, used to our advantage if the cation is stable, right? You can just add that in just like that. Another example, right, is, hey, maybe I have this chloride here, right? Maybe I'm okay with the fact that it adds on that secondary carbon, right? So we'll get this will fall off, right? So what we get out, secondary cation, we'll get the attack there. So again, maybe I am okay with that fact, right? Maybe I've come to terms with it and I'm okay with it. So we'll go ahead and add that there. This one is probably stumped a lot of you because it's on your homework. This one, it may not make sense why it works, because you might think, oh, that isn't that, primary, right? Shouldn't that work? Well, if I draw the cation here, right, what you'll notice is that this cation actually is in resonance. So the only type of primary cation that's allowed is a resonating primary. This is one of those examples. So this is a modification. I guess we can make a modification of it where it has like that tail on it. Oops, sorry, not that, this. Right. Although this would be a difficult one, actually, now that I think about it, this is difficult because you don't know whether it attacks this primary cation or attacks the secondary cation. So if I were you guys, what I would do here, if I were given a problem like this, is I would draw the answer to both. So in one case, you have the addition of where it adds to the primary carbon. Sorry, let me give myself a little more space there. So adds to the primary carbon like that. And then there's the other one where it adds to the secondary, right? So I'll draw it like here, like that. Okay. So if I were you guys, I would draw both. In a case where a resonating primary or a resonating cation can make 2 different types of cations, I would draw both answers. Then there is an example of this actually. This could be a very good, conceptual question to ask you guys, is to give you guys this here, an AlCl3, or sorry, I keep using Al. Let's use Fe this time. Right. And so in this case, right, when I draw the cation, you might think, why is that cation good, right? Well, it's right next to a benzene ring, which we just said is aromatic. It stabilizes, it has resonance, right? Can resonate with that cation. Very, very good. This is a very, very good cation. Okay, it's a very good shibazine there. And when benzene attacks this, it'll attack there. And so you can imagine we can form this here. Okay. So it's like benzene glasses, kind of. All right. So with that, right, again, always with your straight chains, with your N chains, where it's just a bunch of long carbon chains. Always look out for that cation rearrangement. Sorry, over here, right? Look out for that cation rearrangement. But also, I mean, if it can already form a good cation, just let it form it, right? That's totally fine. I don't know if you guys seen this in class, but there are other ways to generate this electrophile. One of those ways is, to use an alkene. So let's say that I had an alkene and I put in something acidic like HF. All HF can do is protonate this alkene here, right? Remember, aromatic alkenes don't want acid, but non-aromatic alkenes, so this alkene here can totally take acid. They'll form this cation. And again, because the Friedel-Crafts electrophile is just a cation, benzene will just go ahead and attack it. So what we'll get is something like that. Okay. Now, there are some things you just need to know conceptually about Friedel-Crafts that also make it bad, right? So one thing that we kind of talked about is that it rearranges. So really only useful in making branch centers or branching alkyls. Okay, so what do I mean by that if that doesn't make sense, right? If you look at every single alkyl center we've kind of formed on that benzene, you'll notice that they always have some kind of branching going on, right? So those guys are branched, those guys are branched, branching there, branching there, branching there, right? This is a very good reaction for making a branch center. So a carbon that is like tertiary or quaternary, right? So tertiary or quaternary at benzylic position. Benzylic position means that position right next to the benzene. So all those places where I put that green dot, that is a benzylic position, right? So this reaction is very, very, very good at doing that, okay? So if that's what you want, right, then totally go ahead and do that. But it's really hard to make a product from alkylation where it's just like that, right? Making that N-propyl species earlier, right? Maybe that was our point. That's going to be hard to make. Or I know we did the N-butyl version, right? Making that is going to be very hard to make. Alkylations are not going to be able to afford those products, right? Because they're always going to want to make branch centers, right? These are not branching centers. So that's not something that I would want to do an alkylation to achieve. Okay, so that's one problem. Another problem is over-alkylation. Okay, so what does this mean? What is an over-alkylation? So it turns out that actually, if I do all the reactions that I just wrote on the previous pages, especially that first one, CH3Cl, AlCl3, turns out that not only do I get one addition of this CH3, but actually this will continue to react. Because CH3s are, in the second half of this video that we'll cover, are something we call activator groups. So what they do is they activate positions right next to and across from them. They give those positions electrons, and it turns out that actually, because these guys are activated, they're more reactive than the original benzene, and they will react with the electrophile faster than the original benzene. So you'll actually get a bunch of products here. Okay, so not only will you get this, you'll also get this and this, and possibly even a trialkyl product, because again, the more of these that you add, the more you activate this system to go kind of haywire and kind of do whatever it wants, which is kind of annoying, but it's just how it is. Okay, so we also see this problem with the branched ones, although typically with the branches, you only really see like one type of product. So for example, let's say that I did this. Right, so, oh, sorry, not that. We would get this here. But because these branches are also a little bulky, you usually only get the disub where they're both opposite from each other. You don't really see this one here, where they're next to each other, right? That's a big no-no. Again, we'll talk about this when we talk about directing effects in the second half, and also the steric effects that we can have with directing effects. Okay. So just something to keep in mind. Right, that this is a possibility. I don't really know what this means for you guys on the quiz. Right, it's up to Dr. Levens to kind of determine how she wants you guys to deal with that. But for those of you that are worried, if you do get a Friedel-Crafts alkylation, you can go ahead and draw the multiple alkylation products. I know that she'll accept them as long as they make sense, right? Like if you put this, and then you put this, and then if it's not bulky and you put this, right, you can get away with those three. She might even expect you to put those three because, again, those are, those are like the expected over alkylations, right? And she probably went over this in class too. It's just when it's bulky that you don't really see them next to each other, but it's possible. I don't know if a trialkyl is possible for this system though. I think that it's, only methyl is the one that makes appreciable amount of this, but whatever. As long as you show that you understand polyalkylation, you should be fine. But, that's something to ask her if she wants you to expect to draw out a polyalkylation if she gives you a Friedel-Crafts. Okay. So 1, rearranges too much. 2, it overalkylates. The third is actually something really interesting. And again, second half type vibes here. But meta directors do not add Friedel-Crafts electrophiles. Okay. So when I say meta director, what I mean, or what you'll learn is that I mean something that's deactivating, but I'll just put here meta. If you have something on your ring that you determine is going to direct something meta, and you see any kind of Friedel-Crafts, so whether it's this or eventually what we'll see is this, right? Neither of these will work. So classic NR problem. And this doesn't really have a solution. We will see that the overalkylation and the rearrangements will be fixed with the acylation, but I mean, you can see here, even acylations won't work. So there's no real solution to this. You just don't do it, this reaction. Okay, cool. So that's the Friedel-Crafts alkylation, really the longest and the toughest one. And what probably took a majority of this hour was to solve that problem. But hopefully now you guys are familiar with that. And again, just for sake of time and just because you have homework and practice, again, we're just trying to go over the concepts so you can see them, right? One last thing that we're going to see again, over and over and over and over and over and over and over again, right? The intramolecularity, molecularity, right? The ability to react with yourself, right? You can totally do this with a Friedel-Crafts. So usually 2 manifestations of this, right? One is that you already have the alkyl chloride attached to the benzene ring. And so in this case, when the metal attacks, I know this one was giving people a hard time on the homework because it was like, oh my God, do I cyclize from here immediately or do I do a shift? We'll just do both, right? Because that doesn't hurt to do both. But let's say that there's not enough time for cyclization, right? Always the carbon next door is what's going to attack the chain. So 1 will attack 2 here, then 3, 4, 5, and then 6. So this will make a 6-membered ring right next door, right? Where it counts as 1, 2, 3, 4, 5, and 6. So if there's anything on here, you can trace it. Methyl on 5, that goes there. Dimethyl on 3, that goes there, right? Stuff like that. But let's say that you're in the camp of, I think that the shift happens faster, or I guess you're in the camp of the homework, because that's what the homework was arguing. You can also go ahead and do that, right? You can say, okay, right, there is a, there would be a chlorine, and that's one metal here, right? We get rid of that. There would be a cation here, and then we switch the cation and the hydrogen, and then we can erase the hydrogen. And now we do our cyclization. Again, you don't have to do this method. Really, the reason why I always go out of my way to do these methods is because I know that there's always a group of people in this class that have a hard time visualizing things, or they have a hard time doing these things. And I really do want to give tips to people that, take the effort to watch these and try to understand the chemistry, and also just, get a way to quickly determine what is the correct answer. Because, it doesn't hurt to see a way to do this that's, usually 99% correct. Okay, cool. So again, we can kind of go around and see if there's anything left over. Looks like there's a methyl on 2 here, so we'll just go ahead and throw that guy down here. Okay, cool. So intramolecularity, that's one way we can see it. We can see it adding, if the chain is already on there, right? We just got to kind of collapse it in, form our ring there, and now you know how to count it, right? Always count from the next door carbon over. You can also see it in the way of, just having a dialkyl dichloro substitution. 1, 2, 3, 4, 5, 6. Okay, that's too many. 1, 2, and then 3, 4, 5. Okay, this is good enough. Right, you can see something like this, and then AlCl3 or something. Right. Again, what this is going to do essentially is, not that it's going to form them both at the same time, but you'll eventually, get this cation here. Or I guess it'll do it probably one at a time, right? So you'll probably make this cation, which the benzene attacks. So is that 1, 2, 3? So 1, 2, 3. And then there's a chlorine here, and then there's a dimethyl. And then we'll do it again, right? Where the chlorine here turns into a cation, and then this just cyclizes, right? So 1, 2, 3, 4, and then 5. That should be a 5-membered ring. 1, 2, 3, 4, and 5. Oops, wrong color. Okay, where 4 has a dimethyl and then 2 has a dimethyl. Okay, something like that. Okay, so these are the usual suspects for your intermolecular reactions. Just be very comfortable with them. Again, you've hopefully seen them on the homework, and now you've seen them here, so it's in your brain. I would say these are note card examples. These are examples I put on the note card, so I don't have to worry about them, right? We will see this one more time, and you can imagine where we're going to see it, right? Which reaction we're going to see it in. So we'll see it one more time. Okay. But yeah, that's the Friedel-Crafts alkylation. So what's the solution, right? We have, something with 3 issues. 2 of them should be solvable. The last one really can. What's the solution? The solution is just take that alkyl chain and turn it into an acyl. Okay. So what we do here now is the acylation. So how does this work? Again, I have a metal. And, you guys don't really need to know this, but it is important to know. But actually, the first step isn't complexation with the chlorine lone pair. It's actually with the oxygen lone pair. Oxygen is really good at making metal bonds. So actually, the first thing that will happen is the oxygen will complex with the AlCl3. Okay. And then over time, very, very slowly, right, the acyl will, the Al will move over to the chloride. Okay. So very, very slowly, this is what's going to happen. Now, when it does happen, so when the chloride does attach, this is the part that makes this reaction a bit irreversible, right? Or what it's sort of like how it pushes the reaction forward. Because the second this chlorine adds to the AlCl3, it's going to depart. And by departing, it forms this cation here, okay, which we call the acylium ion. Okay, so again, aluminum and oxygen metal bonds is very great. So the first thing that happens is that, but slowly over time, we'll start to see conversion. We'll start to see it turn into the adduct with the Cl. And when it does, the chlorine is just going to pop right off. Okay, and it forms this acylium. So what is it with this acylium that makes it so good? Well, it turns out this acylium is not only able to form, it's also resonance stabilized. So this can actually come down and turn into a triple bond version. And it's this triple bond version that's the reason for why we don't see any rearrangements. Because we have something that is stored in the oxygen. We have the cation stored in the oxygen. Okay, it is stabilized in the oxygen via resonance. So no rearrangements will occur because the cation stays put. It's happy where it's at. Okay, that's what the acylium ion allows us to do. And so when the benzene comes along and finds its acylium, right, it's going to attack on that carbon and give us, again, I'm not going to show the elimination. I've shown it a couple times now. It's always the same, just for the sake of time. But it's going to give us this acylated benzene here. And so that's how we get acyl groups on the benzene. Now, one thing that's really interesting about this reaction is that we actually have a second step here. We have an acid step. And a lot of people always wonder why we do that. Well, looking at this product, I want you guys to consider what can happen that might need a hydrolytic workup. What can maybe happen with the carbonyl O that we might have described earlier? Turns out, just like before, in the case of oxygen complexating first with the aluminum, it's exactly what we see happening again. When we form the acylium, once we acylated the benzene with the acylium, the aluminum comes back and makes that same complex with the oxygen of the carbonyl. And so this is the reason why we tend to do two things. It's the reason why we do a workup, because workup is what breaks this. So hydrolysis is what's going to break this bond here and make it into not the aluminum adduct. It'll give us the acylated product. Okay. Also, we need to use one whole equivalent of the aluminum chloride in order to do this reaction. Because normally with all these reactions, that thing under the line, the aluminum or the H2SO4, it's usually catalytic, right? Let's see, how can I show that here? When was the last time I drew that arrow in? It's been a while now, hasn't it? Here, right? When the metal donates a chloride, right? So when the FeCl4 donates a chloride to do this acid base, what we get back is the FeCl3. So in a sense, or not really in a sense, it is, right? The metal allylic acid is usually catalytic. So all these here actually should have said catalytic next to them, because you don't need a lot. You just need a little bit to catalyze the reaction. Here though, because we're losing that aluminum to the oxygen every single time, or even iron, it could have been iron too. Right? It could have been iron there as well. Because we're losing the metal to the oxygen, we have to put in a full equivalent so that every single carbonyl gets a chance to react. Right? Every single acyl chloride needs a chance to react. Right? That's the only way we'll get that to happen. Okay. Cool. All right. Well, that's the acylation. And again, this thing here is what gives us the ability to not have rearrangement. So for this type of reaction, it truly is that if you have an acyl chloride with some group on it, doesn't matter what it is, as long as it has some group on it, right? All you have to do to correctly predict the product is you just replace the chlorine with the benzene ring. And that will work every single time. Doesn't matter what it is. It could even be this here. Oops, sorry. It could even be that there, right? I know there should be hydrolysis. I'm just being lazy. Right. Same thing here. All you're doing is you're going to redraw the chloride, get rid of chlorine, make it a benzene. Wow, look at that, right? The ability to do acylations significantly simplifies things, right? Because you're, again, just replacing. Right? What if I have this, right? What if this is my reagent? Right? What is it going to turn into? Right? Just going to draw the same thing. Just replace the chlorine with the benzene. Again, as long as the benzene is naked, this works 100% of the time, this method. Right? Another way to just think about it is you're just adding this part here, right? You're just adding that part there to the benzene. That's all you're really doing. Everything but the chloride. Okay, cool. Now, I already know a couple of you are thinking, well, Jim, you said that this solves the issue of non-rearrangement, and that it also, that should also mean that it solves making those non-branch centers. So just a reminder, right? Friedel-Crafts alkylation is only useful for tertiary quaternary centers of the benzylic, right? So it's only useful if at this carbon you want branching, right? Remember, we said that it's kind of impossible with alkylation to make these guys here, right? Where we have no branching at all, just a primary center. So how is it that acylation solves this problem if we get a carbonyl? Well, what you can do, let's say that we make this guy here and we want to turn it into this guy here, right? So that we can have that primary center. What you can do is a very simple reduction. There's a couple of them. It'll depend on whatever you see in lecture. But you can do zinc, mercury, and HCl. Or you can do like an H2PD. Either one of these will work, and they will just completely get rid of the carbonyl. Okay, so we still do have access to the alkyl chain, right? We do have an answer to that question. We just have to add an extra step, right? Because we got to get rid of that. Because this ketone is next to the carbonyl, that's what makes it sort of active, sort of makes it, special, and allow it to, hydrogenate or reduce itself completely. This is not something you'll see happening very easily at all when we get to carbonyl's next unit. So something to keep in mind, this is a very special reaction. Let's say that you realize you messed up. You can actually undo this. You can use CrO3 in acetic acid. So CH3 COH, do it at room temp. That will return back the carbonyl actually. I'll put a star here. This will depend on if she teaches you that. I'm pretty sure she teaches you these two though. Maybe I'll put a star on all of this. I'm actually not sure now. So why is it I mean, you should know this. It's a solution. So you should know how to what the answer to that solution is. Okay. Cool. Well, with that being said then, oh wait, actually no, we still have to go over the intermolecularity. Yeah. So just still a little more intermolecular. I mean, this is pretty simple, right? You just have like an acyl chloride out there. I guess this is where it's a little difficult, right? Because it's like you can't use the trick that I mentioned, but that's okay. Because again, it's just a matter of attacking. So one will always attack at the carbonyl. So this makes a 5-membered ring. Where on to, there's a carbonyl. That's always going to be the case. Again, you could do the dicarbonyl kind of thing. I'll kind of try to draw it in a way that suggests what the shape should be. Right, you can kind of see how this is going to glue together, hopefully. Right, it's just you replace the benzene with the chloride, so you can see hopefully it'll click on like that. Nothing too shabby, right? Just making sure you understand that there. Here's actually, here's a question that if you really want to, you can pause and think about this. This is a very good conceptual question. But let's say that we had this species here and we had AlCl3. A very good question could be, what the product of this reaction would be. A very good conceptual question at that. So maybe pause and take a second if you want to think about it. It's okay if you don't, because again, it's a hard question. This is more of like a 128 level question, maybe 118. But hey, I think 8 students could answer this easily because you guys are a smart bunch. So what I would consider in this problem, right, when I'm thinking about this is, what is the AlCl3 going to do in this case, right? There's 2 of these chlorines here, right? One of them has to react with it. Maybe I'm not sure which one. So let's go ahead and consider both of them. So we can consider AlCl3 reacting here, right? And we could consider AlCl3 reacting here. Okay. I'll just put, just for the sake of clarity and because we don't really need it, I'll get rid of the Cls over there. But these are essentially the 2 activation states that are possible. And the question is which one is better, right? I mean, here we do have a substrate that's pretty activated for SN2, right? Again, the chlorine's got to add and then the benzene's got to be enticed to attack. So possibly we get an SN2 there. On the other hand, though, when the AlCl3, right, adds to the chlorine on the acyl, we said that something always happens, right? So we go back here. We said that something always happens the second the Cl adds, and it's what kind of pushes the reaction forward. When the Cl adds the AlCl3, always it leaves, because when it does, it forms the acylium ion, which is way more activated for attack than the alkylation version, right? Or just an alkyl chloride, right? Because we do have a cation, but that cation is stabilized. So it's stabilized enough to exist, but it's still a cation that wants to react. Okay. So in this case, right, the more reactive intermediate or more possible intermediate to be this guy, because the second it forms, this is going to leave. Okay. You can think about it as the AlCl3 kind of juggles between these two. It can kind of juggle. And then, once it, maybe not juggle, maybe what you can think is it comes here first. And then the second it kind of juggles over to the other chlorine, onto that acyl chlorine, it falls off instantly, which forces it to be like irreversible. And what we get out is the acyl cation. Which again, this cation is possible to form because of the fact that it's stabilized. But it's still a cation, so it's still pretty reactive. right? So the position that we're going to attack at is going to be at the chloride. And so what we're going to get from this is this here. Okay. As opposed to the other product, we're not going to see any. Well, not that we're not going to see any, but we're not very likely to see much of this product here. Okay. That regioisomer is probably not going to form. Okay. Again, that's like a higher level question. It's just the way to make sure your conceptual thoughts are in place. By no means is that indicative of the level question you're going to get on your quiz, but it's good one to think about. Okay, cool. All right, well, with that being said now, we have basically covered the first half of the material, which is all the reactions. Hopefully, again, this talk through helps you organize your thoughts. I mean, you can see how quickly we went through these two. I don't know how quickly we went through in class, but the dehydrations don't really need much talk, right? These two are just going to be take out water and add them on, right? So understand what groups you're adding on. It's these three here, specifically the middle one that requires a little more talking about, right? I think the first and the last are kind of easy. It's that middle one that you got to be like, oh, I got to go through and really understand every example. So if there's anything I'd practice if I were you guys, it's the alkylation reactions. Make sure you have those in order. And then again, intramolecularity, right? Maybe I didn't cover something, but it's okay because I said the word, so it should be in your brain now. And you can go back and look at practice problems and see how she could ask intramolecular questions. And also just think about it, right? Like anytime you see that sort of nucleophile and electrophile kind of tethered together, right? So in this case here, or in this case here, they're tethered together. It's some kind of ring form reaction is going to happen, and it's no different on this quiz here. Okay, cool. So in my opinion, that's a lot of information. That's 5 reactions of information. It's a lot. I think you guys should take a break now. I think it's been a good hour, or maybe a little less than an hour, which means that we're actually on a pace today, which is great. I thought we weren't going to be on pace, but I'm happy that we are. So take a second, take a breather. The next half of the material, it's again conceptual, but not too bad. It's going to be directing effects when we're adding multiple things onto a benzene, and how things go. I'm going to go ahead and take a break. I think I might just go to the gym or something. I'll be back. So yeah, cool. All right, I will see you guys then.